Hello, beta. Good evening. Sorry, I missed out today. I was down with viral fever. So I just went in to get the medicines and totally missed out. I thought I have a class tomorrow. So good, you reminded me.
गुड
सर आपका
इवनिंग
तबीयत खराब है तो कल क्यों पढ़ते हैं सर? आपका
Good
तबीयत
evening,
हाँ
sir.
सर, पेयर क्लासेस है सर, ध्यान दीजिए अपना।
नहीं, it's okay, beta.
हाँ सर,
It is
हाँ
okay.
सर, नो सर, अपना ध्यान रखिए सर।
It is okay.
पढ़ेगी
Yes, sir.
आप।
नहीं सर, अरे ओके नहीं है सर, अब कोई बात नहीं, कल ले लेंगे सर, कोई बात नहीं, आराम कीजिए सर आप।
अब आराम
नहीं
कीजिए,
बेटा,
कल करते हैं
नहीं,
सर। हम
नहीं,
लोग को
नहीं
no,
सर,
डॉट भी आ जाएगी।
आधा टाइम निकल गया सर, ध्यान
सर,
दीजिए
गुरु
सर,
को
ठीक है।
फर्स्ट नहीं करना जाता, कल करते हैं।
बात मानो सर।
कल करते हैं सर, आज छोड़ दो।
सर को बोलने दो भाई, सर को बोलने दो।
बेटा मैंने अभी मेडिसिन ली हुई है, so it is fine. अब तुम लोगों ने कनेक्ट कर लिया है. Let us cover something today. जितना पॉसिबल होगा आज करते हैं. Maybe we'll leave early today. Okay.
1 घंटे की क्लास हो रहा है।
तो कुछ
Okay.
डाउट था, डाउट पूछे सर आज।
ओके
डॉट छोड़
बेटा,
दो,
ऐसा
आज छोड़
करते
दो।
हैं.
सर का तबियत खराब है, डॉट छोड़ दो।
अरे डाउट
कल
वो जो
करेंगे, आज
स्टार्टिंग
सर का टॉपिक कर लेते हैं।
सर को आज का टॉपिक कर लेते हैं।
टॉपिक
आज का टॉपिक ये कर लेते हैं. लेट मी एक्सप्लेन यू द टॉपिक एंड डाउट्स कल के लिए रख लेते हैं.
यस सर।
ओके, डाउट्स कल के लिए रख लेते हैं. लेट मी कवर अप द टॉपिक. मुझे आपको छोटे छोटे हमारे टॉपिक्स हैं. वन इज स्टेलर मैग्नीट्यूड, अनदर इज केपलर्स लॉज एंड थर्ड इज चार्ट कंस्ट्रक्शन. ये मैं आपको एक बार कवर करा दूं. सो डाउट्स वी कैन टेक टुमारो. ओके ओके बेटा, ओके ग्रेट. जस्ट गिव मी अ मिनट, मैं प्रेजेंटेशन सेटअप करता हूँ.
सर वो असाइनमेंट में जो एक सर असाइनमेंट के डाउट्स आप कल क्लियर करेंगे?
हाँ बेटा, कल क्लियर कर लेंगे. लेट अस कीप डाउट्स फॉर टुमारो. कुछ एक डाउट्स हो सकता है आपके अभी क्लियर हो जाएं जो मैं टॉपिक्स पिकअप कर रहा
सर
हूँ.
बस वही वो जो ग्रीनविच का आपको मैंने पूछा था, वो कि ग्रीनविच का पोजीशन कैसा है, वो थोड़ा डाउट आ रहा था।
ओके 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 ओके. वो
चलो
तो
सर
बहुत
कल कर लेंगे आराम से।
You're right. I'll explain you. That's very simple to understand. So let me put up the presentation now. इसमें बेटा सबसे पहले मैं आपको एक स्टेलर मैग्नीट्यूड का क्वेश्चन कभी कभी आता है जिसमें हमें ना लॉग का फॉर्मूला लगाना पड़ता है, वो एक्सप्लेन कर रहा हूँ. और फिर इसके बाद मैं आपको लेके जाऊँगा केपलर्स लॉज पे. सो उसकी थ्योरी भी आती है, उस पर बेस्ड न्यूमेरिकल्स भी आते हैं. एंड थर्ड चीज़ हम करेंगे चार्ट कंस्ट्रक्शन. सो लेट्स गो. लेट मी पुट अप द प्रेजेंटेशन. सबसे पहले चल रहे हैं बेटा स्टेलर मैग्नीट्यूड क्वेश्चन पे.
Now, the first concept which we are going to look into is the concept of stellar magnitude. Now, we are aware stellar magnitude is basically a scale which gives us the apparent or relative brightness of different celestial bodies. Let's see the question. The question says star A has a magnitude of -0.8 and it is 30 times brighter than star B. Find the magnitude of star B. Now, all these questions which we are discussing are picked up from the past papers. So let us see how do we attempt this question. Now, for doing this question, we need to be aware of two things. Number one, that the stellar magnitude gives us a formula or a relationship with which we can find out how many times a particular body is brighter or dimmer than the other body. What is that formula? The number of times a star is brighter than the other is given by the formula 2.51 raised to power the difference of their magnitudes. So this is the formula which we will be using in this question. Now, second concept which we need to be aware of, which we have done in our school time, That is a logarithmic concept. That formula, logarithmic formula, is log of a raised to power b is equal to b multiplied by log of a. So this is a logarithmic formula which we will be using, which we need to use to solve this particular question. So once we are aware of these two things, the question can now be solved. First of all, let's assume that the difference of magnitudes between the two bodies is x. If the difference of magnitude between the two stars, star A and star B, is x, that tells us 2.51 raised to power x should be equal to how many times one star is brighter than the other. Now this is given to us in the question. The question says that star A is 30 times brighter than star B. So this tells us 2.51 raised to power x is equal to 30. Now we want to solve this relationship for x. So for this, what we do is we take a log on both the sides. So this gives us log of 2.51 raised to power x is equal to log of 30. Now applying the logarithmic formula which we saw, log of a raised to power b is equal to b multiplied by log a. Similarly, you see log of 2.51 raised to power x is equal to x multiplied by log of 2.51, and this is equal to log of 30. Now keeping x on one side and taking the other items on the opposite side, we get x is equal to log 30 upon log of 2.51. We can easily solve this using our scientific calculators. So when we solve this for x, it gives us the value as 3.6958. So this x, which was assumed to be the difference of magnitude between star A and B, has been found to be 3.6958. Now it is given that the magnitude of star A is minus 0.8. The difference is 3.6958. And since star B is dimmer, it is given in the question, star A is 30 times brighter than star B. So this tells us that the star B is a dimmer star. Now, since it is dimmer or less bright, its magnitude number will be greater than the magnitude number of A. We know that the stellar magnitude scale is a reverse logarithmic scale. That means as the brightness increases, the magnitude decreases. And as the brightness goes down, the magnitude number increases. So this tells us that star B, which is dimmer, its magnitude number should be greater than the magnitude of A. So magnitude of A was minus 0.8. Between the two is 3.6958. This is the difference between magnitudes of A and B, and magnitude of B has to be greater than the magnitude of A. So what we do is we add this difference 3.6958 to the magnitude of A, which is minus 0.8, giving us a value of 2.8958. So this is the magnitude of star B. So you can see now star B magnitude 2.8958, star A magnitude is minus 0.8. The difference between both of them is 3.6958. And if you use that difference in this equation, 2.51 raised to power this difference, it will give you the value of 30. So this is how the question is solved.
So is it clear, beta? Any doubts in this?
नो सर.
नो सर.
वेरी गुड बेटा, ग्रेट. ये आपको याद रखना पड़ेगा फॉर्मूला. सो ग्रेट. So let's move on to the Kepler's laws now. This was stellar magnitude.
Sir, from stellar magnitude only this basics question will be asked, or is there some advanced version also?
बेटा ये जो मैंने आपको करवाया ये कॉम्प्लिकेटेड वाला है. बेसिक वाले में तो ये आपको दो ऑब्जेक्ट्स का स्टेलर मैग्नीट्यूड दे सकते हैं एंड दे विल टेल यू टू कैलकुलेट हाउ मेनी टाइम्स वन ऑब्जेक्ट इज ब्राइटर देन द अदर. तो उसमें तो सीधा ये फार्मूला यूज करना है 2.51 रेज टू पावर द डिफरेंस एंड दैट विल गिव यू द आंसर.
सर एक x करके मानते हैं, जो x से एक क्वेश्चन वो भी आता है, x का इतना ब्राइटर है, y का इतना कुछ तो मतलब वैल्यू नहीं दिया रहता है. मैं देखता हूँ क्वेश्चन फिर शेयर करता हूँ.
वो ऐसा ही क्वेश्चन है बेटा, आप उसको इसी मेथड के साथ सॉल्व कर पाओगे.
सही.
ओके ओके सर.
तो असाइनमेंट में सारे क्वेश्चंस दिए हुए ना ऐसे टाइप के.
या असाइनमेंट दिस इज देयर बेटा, यू विल फाइंड दिस इन द असाइनमेंट. जो भी मैं आपको यहाँ करवा रहा हूँ ये आपको असाइनमेंट में नंबर 1 to 11 में मिल जाएंगे.
सर मैं वो सर बाद में पूछना वो दूसरे टॉपिक से रिलेटेड.
ओके ऑल राइट बेटा, लेट्स मूव अहेड.
Now moving further, the next set of questions is based on Kepler's laws of planetary motion. So there are three laws which basically give us an idea about the motion of planets around the sun in the solar system. So before we go into the numerical, let us discuss about the Kepler's three laws of planetary motion. The first law of Kepler states that all the planets revolve around the sun in elliptical orbits. So as you can see, we have this blue color planet revolving around the sun in an elliptical orbit. The green color orbit which we see in the diagram is having elliptical shape. Now before Kepler, people used to believe that the orbits of planets are circular, but Kepler's with his observations proved that these orbits are not circular but elliptical. Though the ellipticity of these orbits is very less, they are very close to a circular shape, but still they are not exactly a circle, they are not exactly circular, they are actually elliptical. Now just as a circle has one center, the ellipse on the other hand has two reference points, and these reference points are known as focus. So it has focus 1 and focus 2. In plural it is known as foci. So all the planets revolve around the sun in elliptical orbits. Every elliptical orbit has two foci, and sun is situated at one of the foci of the ellipse. The other foci is blank, there is nothing there, but sun is situated at one of the foci of the elliptical orbit of all the planets. This is Kepler's first law.
Is that clear beta?
Yes, sir.
Very good beta, great.
Now moving on to Kepler's second law. Kepler's second law states that the radius vector of a planet sweeps out equal areas in equal intervals of time. Let us understand with the help of a diagram. We see the sun as the yellow circle in the middle of the diagram, and then we see a elliptical orbit of a particular planet, and in this elliptical orbit, let us assume that on a particular day when we started our observation, the planet was at this particular location. You can follow the laser pointer. So let us assume that on one particular day when we started observing the planet was at this particular location where the laser pointer is right now. Now, if the planet is at this location, the radius vector of the planet is this one. You can follow the laser pointer. This is the radius vector of the planet. Now, after that, the planet starts to move. We keep on observing the planet day after day. And let us say after 30 days, we again make our observation and the planet has reached up to here. Now, in this interval of 30 days, the radius vector of the planet has covered an area which is shaded in blue. This is the area swept by the radius vector of the planet in a duration of 30 days. Now, after this, the planet, we stop our observation. The planet keeps on moving on its orbit. Now, when you are moving on an elliptical orbit, at some places you will be far away from the foci, which is basically the sun, and at some places you will go closer to the foci. In a circle, all the points on the circumference are equidistant from the center, but in an ellipse, the track of the ellipse sometimes goes closer to the foci, to a particular foci, and sometimes goes away from the foci. So the planet moves further and it reaches at this particular location where the laser pointer is right now on a certain day, and we start our observation again. Now we start our observation. This is the radius vector of the planet right now. The planet continues to move and we keep observing the planet for the same duration of 30 days. Now, after 30 days, we observe that the planet has reached up to this particular point. And you can see this is the radius vector of the planet now. The area which is swept by the radius vector of the planet in the same duration of 30 days is represented by this blue color sector. So you can see the two different sectors as the areas swept out by the radius vector of a planet during its two different locations in its orbit. Now Kepler said that the area swept out by the radius vector of the planet in equal intervals of time will be equal. So the area of this blue sector will be equal to the area of this blue color sector. Both their areas are going to be same. Now, what does this tell us about the motion of the planets in its orbit? Now, if the planet has to sweep out equal areas in equal intervals of time, the planet will have to move faster in its orbit when it is closer to the sun. You see, at this particular location, the planet is much closer to the sun as compared to the previous observation. So with the planet being much closer to the sun, you see the length of the radius vector is much smaller as compared to the previous case. Now with the length of radius vector being much smaller, if it has to sweep out equal area, it has to move at a much faster pace or much faster speed in its orbit. Now, when the planet is far away from the sun in this particular condition, you can see the radius vector is very, very long as compared to the radius vector in the previous instance. Now, with the radius vector very, very long, if it has to sweep out equal area in equal interval of time, the radius vector or the planet has to move very slowly in this part of its orbit. So, it gives us an indication that the planet moves faster when it is closer to the sun. You can see this is the sector where it is closer to the sun, and the planet has moved quite fast in its orbit. And when the planet is far away from the sun, it will move very slowly as compared to the previous instance. So the motion of the planet or the speed with which it covers its orbit is not constant or fixed. The planet keeps on changing its speed. It becomes slow when it is far away from the sun, and it gains speed, it picks up speed and becomes faster when it is closer to the sun. So this is Kepler's second law of planetary motion. The radius vector of a planet sweeps out equal areas in equal intervals of time, indicating to us that the planet will be moving faster in its orbit when it is closer to the sun, and it will be moving slower in its orbit when it is farther away from the sun.
Any doubts in this, beta?
No, sir.
Very good, beta. Great. Let's move on.
Now moving on to Kepler's third law of planetary motion. Kepler's third law basically gives us the relationship between the mean distance of a planet from the sun, which is also known as its orbital radius, represented by alphabet R, and the time it takes to complete one revolution around the sun, which is also known as its orbital period, represented by alphabet T. So the third law gives us a relationship between the orbital radius and the orbital period of a particular planet. What does the law say? The law says that the square of a planet's orbital period is proportional to the cube of the mean distance of the planet from the sun. In other words, T square is proportional to R cube. It can be denoted in this particular relationship. T square upon R cube is constant, can be considered as K. T is the orbital period of a planet. Let's say, for example, if you take the case of the Earth. So in the case of Earth, the orbital period is 365.25 days. And R is the orbital radius, mean orbital radius of a planet. In case of Earth, the mean orbital radius of the Earth's orbit around the sun is 93 million miles, or 93 into 10 raised to power 6 miles. So this is the relationship given by Kepler's third law of planetary motion. T square by R cube is equal to constant. This is a very important relationship, and we get numerical question based on this particular relationship.
Moving ahead now.
Now, how can we utilize this relationship in the numerical questions? Now, for using this relationship, we need to be aware of the orbital time, or the time Earth takes to complete one orbit around the sun, and the orbital radius of the Earth. Now, we know that the time period, orbital time period of the Earth is 365.25 days. And we know the orbital radius of the Earth is 93 million miles, which is 93 into 10 raised to power 6 miles. So T square upon R cube of Earth converts to 365.25 square divided by 93 into 10 raised to power 6 cube. This, being constant for each and every planet, should be equal to T square by R cube of any of the planets of the solar system. If you look carefully now in this relationship, T square by R cube of Earth is known to us. If we are given the orbital radius or the orbital time period of any of the planets, one of these two items is provided to us. By using this relationship, we can easily find out the second unknown item. If the orbital time period of a planet is given, we can put that in this relationship and we can obtain its orbital radius. And the opposite is also true. If they provide us with the orbital radius of a particular planet, we should be able to calculate the orbital time period of that particular planet. Now for this, you need to be aware of these two values, the orbital time period of the Earth, 365.25 days, and the mean orbital radius of the Earth, 93 into 10 raised to power 6 miles. These figures are not given in the question. It is expected that the candidate is aware of these figures to be used in a numerical based on the Kepler's laws.
Clear, beta? Any doubts up to here?
No, sir.
Very good, beta. Great. Let's move ahead.
Now, next we refer to some planet configurations. Configurations basically means a particular location of the planet in its orbit. So the terms which are used to represent or show planet configurations are conjunction, number 2 opposition, and number 3 quadrature. They basically tell us about the position of a planet with respect to the sun. Let us now understand all these three configurations or all these three terms with the help of a diagram. Let's show the sun in our diagram. Then around the sun we show planet Earth. I have shown it in blue color. Our Earth is a blue planet. And let's show the orbit of the Earth now. We have the orbit of the Earth on the diagram. Now let's show another planet of the solar system. We show the red planet, and it is the Mars planet. We are aware that the orbit of Mars is greater than the orbit of the Earth. So let's now show the orbit of the Mars. We have the orbit of the Mars in our diagram. Now both Earth and Mars are revolving around the sun in their orbits. The speed at which they are revolving around the sun is different. They are revolving around the sun with different speeds. All the planets have different speeds. We just saw the third law of Kepler's planetary motion, which said t square by r cube is equal to constant. So as the radius keeps on increasing, the time period also keeps on increasing. So that tells us that the angular speed with which the planets revolve around the sun will also keep on changing from planet to planet. Now with varying speed, it is possible that the Earth and a particular planet may be at different locations with respect to the sun. Like for example, right now when you see in the diagram, you can see that for an observer on the Earth, the sun as well as the planet Mars are in the same direction. Both the sun and planet Mars are in the same direction. Now this particular placement of the planet with respect to the sun is called as conjunction. We say that this particular planet or planet Mars is in conjunction with the sun. So this is the meaning of the first term, which is conjunction. Basically means that the planet is in the same direction as the sun. The planet is in conjunction with the sun. Now let's say after some time we keep on observing this particular planet, and this particular planet moves to a different placement in its orbit, and right now the planet has moved to this particular placement, this particular location in its orbit. Now for an observer on the Earth with the planet Mars at this particular location, you can see now that the Sun and the planet Mars are opposite to each other, or they are in opposite directions. The Sun is in one particular direction and the planet Mars is exactly in the opposite direction. Now this particular orientation is called as opposition. We say the planet Mars is in opposition to the Sun. So opposition basically means that that particular planet and the Sun are in totally opposite directions. Now let's assume that the planet keeps on moving in its orbit with some relative speed, and at another particular instant we observe that the planet Mars is at this particular placement or location in its orbit. Now if you observe this planet Mars carefully, you see the direction in which the planet Mars is at right angles to the direction in which the Sun is. So whenever a planet is at right angles to the direction in which the Sun is, it is called as quadrature. So this is the planet Mars in quadrature. The direction in which the planet Mars is 90 degrees away from the direction in which the Sun is. Now there is a possibility, another possibility of quadrature. If the planet Mars at a particular instant reaches to this location in the diagram, you can follow the laser pointer. So at this particular location also, the direction in which the planet is at right angles to the direction of the Sun. So it tells us that this particular planet is in quadrature with the Sun. So conjunction means the Sun and a particular planet are in the same direction, or the angle between them is 0. Opposition means that the direction in which the Sun and a particular planet are exactly opposite to each other, or the angle between the Sun and that particular planet is 180. And quadrature means that the direction in which the Sun is 90 degrees away from the direction in which the planet is, or the angle between the Sun and the planet is 90 degrees.
So any doubts in this now, beta?
No doubt, sir.
Very good, beta. Great. Let's move ahead.
Now the next important concept which we have is the concept of elongation. Let's understand what elongation is. Elongation of a planet is the angle at the center of the Earth between the Sun and that particular planet. Let's try to understand it with the help of a diagram. We have the Sun in our screen now. Let's show the planet Earth. We can also mark off the orbit of planet Earth. You can see the orbit of Earth in blue color. Now let's show another planet. In this case, we show planet Venus. Now Venus is closer to the Sun as compared to the Earth. So let's now mark off the radius of the orbit of Venus also. You can see the orbit of Venus in maroon color as shown by the laser pointer. Let's now try to show the radius vector of Venus as well as Earth. So you can see this dotted line joining the center of Sun with the center of the Venus. This marks off the radius vector of planet Venus. Similarly, you can see this blue color dotted line showing the radius of the Earth. Now let's draw another line joining the center of the Earth and the center of the planet Venus. So you can see this red color line joining the center of Earth with the center of Venus. Now from this diagram we can easily understand what elongation is. You see this red highlighted angle in the diagram is what is elongation. Let's try to match with the definition of elongation. The definition says elongation of a planet is the angle at the center of the Earth. You see this red angle is being made at the center of the Earth between the Sun and the planet. So from the center of the Earth, a line joining the center of the Sun and a line joining the center of the Venus, angle between those two lines is the elongation. So angle at the center of the Earth contained between the Sun and that particular planet is known as the elongation of that particular planet. Now, as Earth and Venus are moving with different orbital speeds, different angular velocities in their orbits, their location with respect to each other will keep on changing. The planet Venus could be at any particular elongation depending upon what is its position in its orbit. Let's assume that if planet Venus is at this particular position here, the elongation will be the blue color line showing the radius of the Earth and the line joining the center of the Earth with the location of Venus at this particular point. If Venus is at this particular location here, the elongation will again be by the angle between the radius of the Earth and the line joining the center of Earth with center of the Venus. Now, if you look carefully, that as the planet Venus moves in its orbit, you can follow the laser pointer. At this particular point, Venus will be in conjunction with the Sun, or the elongation will be 0 degrees. Now, as it moves in its orbit, the elongation will start to increase. At this particular point, at the first location, it will have a certain elongation. After this, the elongation will keep on increasing. Now, if you look carefully at this particular point, Venus will have the maximum elongation. The angle at the center of Earth will be maximum at this particular placement of Venus in its orbit. As Venus moves forward in its orbit, you see the elongation will start to reduce again. Now, this point where the maximum elongation occurs, if you look carefully, you will see it is the point where from the center of Earth, if you draw a tangent to the orbit of Venus, the tangent meets the orbit of Venus at this particular point. This is the point where Venus is going to have maximum elongation. And we are aware that the tangent is always perpendicular to the radius of a circle. So this line joining the center of Earth with the center of the Venus, the red dotted line, represents a tangent, and this line joining the center of Sun with the center of Venus represents the radius of the Venus. So they will be at right angles. So this angle here at planet Venus will be 90 degrees. So this is the point of maximum elongation of Venus, and we know at the point of maximum elongation, the angle made at point Venus between the Sun and the Earth would be 90 degrees. Now, this particular diagram is used in solving some of the questions. So you should be clear about the concept of maximum elongation, and what is this angle which is made at the planet at the time of maximum elongation. Now, if you consider a exterior planet means the planet whose radius is greater than the radius of the Earth, like say for example Mars. Now, the maximum elongation of Mars is going to be 180 degrees. The maximum value of elongation is possible, which it can be, is 180 degrees. For a exterior planet like Mars, it can reach up to its maximum elongation, that is 180 degrees, when it is in opposition to the Sun. But for an inferior planet like Mercury or Venus, the maximum elongation will be less than 90 degrees, and it will depend upon the radius of that particular planet and the radius of the Earth. Now, inferior planets like Venus, as you see in this diagram, can never be in opposition to the Sun. They can never be in opposition. Irrespective of whichever position they are in their orbit, they can never go in a direction which is opposite to the direction of the Sun. And at the same time, if you look carefully, you will observe that these inferior planets like Mercury and Venus can also never be in quadrature with the Sun. To be in quadrature, the angle at the center of the Earth or the elongation has to be 90 degrees, which is not possible in this particular case. So opposition and quadrature can only be attained by exterior planets whose radius is greater than the radius of the Earth. And for inferior planets like Mercury and Venus, whose radius is less than the radius of the Earth, they can never be in quadrature and in opposition.
So, any doubts coming in your mind, beta, up to here?
No, sir.
No,
Okay,
sir.
beta. Great.
Clear.
Very good. So let's see a couple of questions which are based on these concepts now.
So, sir, the superior planets which are there, they won't be in conjunction, no?
The inferior planets, beta?
No, the superior ones.
Superior ones can be in conjunction, beta. They can be in the same direction in which the Sun is. They can go on opposite side, na?
Yes, sir. Okay, understood. Yeah, okay.
Okay.
We have learned some concepts related to the motion of the planets in the solar system. Let's now try to see what type of questions are formed on the basis of these concepts. We have the first question now on the screen. Jupiter has an orbit of 11.86 years. This 11.86 years is the orbital time period of Jupiter. Calculate the distance between Earth and Jupiter when Jupiter is in opposition with the Sun. So they told us that Jupiter has a orbital time period of 11.86 years. And they have also told us that Jupiter is in opposition with the Sun, means looking from Earth, Sun and Jupiter are in opposite directions. And we need to find what is the distance between the Earth and Jupiter. Let's try to understand this question using a diagram. Let's make the Earth in our diagram here. We show the orbit of the Earth also. We have the Sun also in our diagram now. And we now know that Jupiter is in opposition with the Sun, means Jupiter is in opposite direction to the direction of the Sun. So Jupiter has to be here. You see, in this particular place. For an observer on the Earth's surface, the Sun and Jupiter are in opposite directions.
सर ये उस तरह भी
Now
हो सकता है
we
ना
can
सर, सन के अपोजिट में वो कंजंक्शन हो जाएगा.
That's right, beta. If you take it to the
Conjunction.
other side of the sun, that will become a conjunction.
कंजंक्शन ओके ओके सर.
Okay.
show the orbit of the Jupiter also in our diagram, and we now need to find out this particular distance, that is the distance between the Earth and the Jupiter. Now how can we obtain this distance? This is what is required. Now if you look carefully, if we join the center of Earth with the center of the Sun, this is the radius of the Earth. It is represented by the blue color line in the diagram. This is the radius of the Earth. And if we measure the distance between the center of the Jupiter to the center of the Sun, which is represented by the red color line in the diagram, which I am highlighting with the laser pointer, is the radius of Jupiter. Now you can clearly see the distance which is required by us is equal to radius of Jupiter minus the radius of Earth. So orbital radius of Earth is known to us. It is 93 million miles. The orbital radius of Jupiter is not known. So is there a way we can find out the orbital radius of the Jupiter? Yes, certainly. We can find that in this question using the Kepler's third law of planetary motion, which says t square by r cube is equal to constant. So you place the t square by r cube of Earth equal to the t square by r cube of planet Jupiter. We have the orbital time period of the Jupiter as 11.86 years. So the only unknown in the equation will be the orbital radius of the Jupiter. So once you get the orbital radius from the relationship, you can subtract radius of Jupiter minus radius of Earth. It will give you the required distance, which is the distance between the Earth and Jupiter.
So is that clear, beta?
Yes, sir.
Okay, great. This is there in the assignment also. Assignment it is solved, so you can match your working there. Great. Let's move on to the next one.
Let's see one more question based on these concepts. The question says, if the sidereal period of Venus is 224.7 days. Sidereal period means the orbital period. Venus takes 224.7 days to complete one orbit around the Sun. So if the sidereal period of Venus is 224.7 days, find its maximum elongation. So let's try to make a diagram to understand how do we proceed in the question. Now we know that elongation is the angle at the center of the Earth contained between the Sun and that particular planet. So let's make a diagram. Let's first show the Sun in our diagram. We can show the Earth next. And we also show the orbit of the Earth in blue. Now let's show the orbit of Venus. We have the Venus planet here. And you can see the orbit of Venus also in the diagram. Now let's join the center of Sun with the center of the Venus. This basically is the radius vector of Venus. And let's now join the center of the Earth with the center of the Sun. This is basically the radius of the Earth. Let's now join the center of Earth and planet Venus also. So you can see this is the particular case or particular condition in which this line joining center of Earth and center of Venus is tangential to the Venus orbit, telling us that Venus is going to attain its maximum elongation at this particular point. And the elongation here is this particular angle, the red color angle which you see, the angle at the center of the Earth between the Sun and the planet Venus. This is what we require. So this is the elongation, maximum elongation of Venus. Now, we are aware that at this point of maximum elongation, the angle at Venus between the Sun and the direction of the Earth has to be 90 degrees, because this line joining the center of Earth with the center of Venus is a tangent to the orbit of Venus, and the line joining Sun and Venus is the radius of this orbit. So tangent and radius are always at right angles, so that's why you see this angle is 90 degrees. Now, if you look carefully in this particular diagram, it is a right angle triangle, and we need to find out the red angle, the elongation. And in this particular diagram, the radius of the Earth is known to us, orbital radius of the Earth, which is 93 million miles, 93 into 10 raised to power 6 miles. And if we also know the radius of Venus, then we can very easily calculate the elongation. How can we calculate it? We know sine theta is equal to perpendicular upon hypotenuse. So if we take sine of elongation, it will be equal to radius of Venus divided by radius of Earth. You see, in this particular triangle, radius of Earth is the hypotenuse. It is the side opposite to the right angle. And the radius of Venus is the perpendicular considering this angle, the red angle. It is opposite to the angle, so it is the perpendicular. So if we have the radius of Venus and the radius of Earth, we can easily find out the elongation using the sine theta relationship. Now, radius of Earth is known to us, radius of Venus is not known, but we can easily calculate the radius of Venus using Kepler's third law of planetary motion, which tells us that t square by r cube is constant. We know the t square and r cube of the Earth, and we also have the sidereal period or the orbital period of Venus as 224.7 days. So when we put this value in the t square by r cube relationship, we can easily find the orbital radius of Venus, and using its orbital radius, the elongation can be easily calculated. So this is how we solve this elongation question. The answer to this question is 46 degrees 19.8 minutes.
सर ये सबके रेडियस याद करने पड़ेंगे?
नहीं बेटा, आपको सिर्फ अर्थ का याद रखना है, 93 मिलियन माइल्स, बाकी तो आप कैलकुलेट करोगे केपलर लॉ से।
जैसे अभी अर्थ का 365 डेज है और लास्ट क्वेश्चन में जुपिटर का 11.87 ईयर्स दे रखा था, तो कुछ
राइट
तो नहीं करना ना हमें?
नहीं बेटा, अगर आपको ईयर्स में उन्होंने टाइम पीरियड दे रखा है तो आप अर्थ के लिए उसे 1 ईयर कंसिडर कर सकते हो। सो इन द फॉर्मूला इन द अर्थ पार्ट यू पुट इट एज 1।
ओके, हम 1 ले लेंगे ना, ठीक है।
राइट बेटा, यू डोंट नीड टू कन्वर्ट इट इनटू डेज, कोई भी यूनिट यूज कर सकते हो, दोनों तरफ सेम यूनिट होने चाहिए।
ओके
ओके बेटा, ग्रेट। So this basically takes care of the Kepler's laws type of. बोलो बेटा।
सर लास्ट क्वेश्चन का आंसर वो थोड़ा बता सकते हैं?
ओके बेटा, ओके। लास्ट का आंसर वो असाइनमेंट में भी है, इट इज सॉल्व्ड देयर एंड द आंसर इज आल्सो देयर, बट इट वाज 390.6 into 10 raised to power 6 miles.
सर
okay, हाँ।
मेरा कुछ अलग आंसर आ रहा है सर इसमें।
क्या आ रहा है बेटा, आपका आंसर क्या आ रहा है?
सर मेरा 9.77 into 10 raised to the power 6 आ रहा है।
ओके ओके, तो बेटा
इसको मैंने
दो चीजें। एक तो इसे जो असाइनमेंट में सॉल्व क्वेश्चंस है उसकी वर्किंग के साथ मैच करके देखना। सेकेंडली अपने कैलकुलेटर में क्यूब रूट, स्क्वायर रूट, इन चीजों को एक बार प्रैक्टिस करके देखना। देयर मे बी सम मिस्टेक इन स्क्वायर रूट और क्यूब रूट।
ओके ओके सर।
ये सही कॉमन मिस्टेक होता है।
राइट, बिकॉज इट बिकम्स ट्रिकी है कैलकुलेटर में। ये बटन्स जब आप यूज करोगे, it is going to get little tricky, so practice these questions.
ओके सर ओके।
Okay, all right. So these were the Kepler's laws questions बेटा। अब बेटा मुझे एक बात बताओ, इसके बाद हम नेक्स्ट अब चलेंगे चार्ट कंस्ट्रक्शन पे। सो shall we move on to the chart construction, या एक छोटी ब्रेक के लिए रुकते हैं यहाँ?
सर ब्रेक लेनी है।
कितना टाइम लगेगा?
ब्रेक लेने है सर, ब्रेक।
ठीक है बेटा, ले लो। ओके, 5 minutes.
ठीक है सर।
Okay, so let's meet back after 5 minutes, then we'll go with chart construction. Okay, beta, are we back? Go ahead, Nelson.
Sir, I've been intending to ask this doubt. Sir, when I was doing this stars suitable for observation with different name for latitude and declination, in the Norris table, the A value for some of them diagonally, it is absent. It is not there. So it is, in that case, it is not suitable for observation, right, sir?
एग्जैक्टली बेटा, आप इस टेबल में देखोगे जो टेबल 1 है उसमें आपको ना एक बैंड दिखाई देगा, डायगोनल काइंड ऑफ बैंड विच इज ब्लैंक. सो अगर वो बैंड में आपकी वैल्यू आ जाती है तो दैट सिंपली टेल्स यू दैट दिस बॉडी इज नॉट सूटेबल फॉर एक्स मेरिडियन.
yes, और दूसरा ये जो कॉकटाट रेजोल्यूशन जो आपने कराया है वो मतलब ये सेलेस्टियल के लिए है, जो चार्टवर्क के लिए जो है उसका अलग मेथड होगा ना सर? उसका
डिफरेंट मेथड बेटा, टोटली डिफरेंट मेथड है. चार्ट वर्क में आप परपेंडिकुलर बाइसेक्टर्स यूज करते हो, सेलनैव में आप एंगल बाइसेक्टर्स यूज करते हो. द मेथड्स आर टोटली डिफरेंट.
ओके सर, परपेंडिकुलर बाइसेक्टर फॉर चार्ट वर्क एंड एंगल बाइसेक्टर.
राइट,
और यस
राइट. हमारे वाले में तो एंगल बाइसेक्टर है. चार्ट वर्क वाले में आई थिंक विष्णु सर का आई सॉ उन्होंने इमेज भी डाली हुई थी ग्रुप पे. So you have to make a triangle with the 2 lighthouses and the intersection point of the bearing. फिर उस triangle के 2 angle bisector बनाने होते हैं. That gives you the center of one circle. Same thing you do with other triangle. You get the second circle and intersection point is the fix.
Okay sir.
Okay. Okay.
सर लास्ट क्वेश्चन का आंसर क्या था सर?
जो elongation वाला था बेटा?
यस सर.
ओके, वैसे असाइनमेंट में ये क्वेश्चन दिया गया है बट इट इज 46 डिग्रीज 19.8.
ओके सर, सही है सर, करेक्ट.
ओके
सर, ये अर्थ रिवोल्यूशन अराउंड द सन कहीं पे दिया है 365.26 और आप कह रहे हो 365.25, तो कौन सा वैल्यू ले सर?
365.25 बेटा, एक्चुअली इट इज स्लाइटली लेस देन दैट. It is about 365.2499, but you can take it as 365.25.
Okay sir.
सर गूगल में 365.25636 दिखा रहा है.
Oh, leave that. No, not required.
तो 65 पे बेसिस तो कर लेंगे सर, आ जाएगा आंसर उससे.
हाँ, 365.25. 0.25 मत छोड़ना बेटा.
ओके.
सर नेविगेशन की बुक है, प्रिंसिपल नेविगेशन, उसमें लिखा है मैक्स डेक्लिनेशन 23 डिग्री 23.5 डिग्रीज. वैसे सन की आती है वो 23 डिग्रीज 27.6.
26.7.
26.7.
हाँ जी, 26.7 सर.
राइट बेटा, अगर आप 23.5 से भी कर दोगे, आई वुड से 90% कोई भी आपको गलत नहीं करेगा. But 26.7 is a more accurate value. So अगर आप इसे यूज करोगे, that will the examiner paper checker will be happy.
ठीक है सर, उसको ही खुश करना सर.
अदरवाइज आंसर्स में कोई खास डिफरेंस नहीं आएगा.
ओके सर.
ओके, ग्रेट बेटा. सो लेट्स मूव ऑन टू चार्ट कंस्ट्रक्शन बेटा. इनके सवाल हमारे पेपर में आते हैं. सो लेट अस सी कि किस टाइप के क्वेश्चन आते हैं, कॉन्सेप्ट क्या है. नाउ ये जो सवाल है बेटा चार्ट कंस्ट्रक्शन